I want you to picture the light switch in your room. How many states does it have? In other words, how many positions does it have? This light switch right here has two positions, on and off. Most light switches do. Some newer ones changed a little bit. But let's also assign those values of a 1 for on and a 0 for off. By the way, if you're ever wondering what the origin of the power symbol is, it's a 1 and a 0. Let's call this a bit. So one switch equals 1 bit. Now that we know what a bit is, what happens if we have 2 bits? How many different combinations of zeros and ones can we have? Let's say for this, the position matters. So switch A turned on and switch B turned off is not the same thing as switch A turned off and switch B turned on. This is pretty easy to enumerate through. We can have A and B off. We can have A off and B on. We can have A on and B off, or we can have A on and B on. This means we have 4 possible combinations. What about if we add another bit? So now instead of 2 bits, we have 3 bits. How many possible combinations do we have now? With 1 bit, we only had 2. With 2 bits, we have 4. So how many do we have with 6? Let's enumerate through this again. Let's start with all zeros. Got 0, 0, 0, and then 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, and 1, 1, 1. So those together gave us 8 possible combinations. With this, I hope you're starting to see a pattern. With each bit we add, we double the amount of possible combinations of ones and zeros, ons and offs. I've mentioned this equation in a previous video, but in order to calculate the amount of potential combinations, we take the number of states possible and raise it to the number of bits that we have. So in this case, we have 2 possible states for each bit, and we have 3 bits. So that's 2 raised to the 3rd power, or 2 times 2 times 2, which gives us 8. So why am I making a big fuss over the number of potential combinations? Well, simply put, we can then say that each group of bits represents a number. You'll see why this can be so powerful in a minute. Consider this number right here. We now have 8 bits, which we'll call a byte. In order to turn a group of bits into a number, we first need to determine where the least significant bit is. Most binary that you encounter, this will be the rightmost bit, right here. It will be noted somewhere if it is elsewhere. This can also be referred to as endianness, but I will leave endianness as an exercise for you to research. Next, we assign a value to each bit starting from the least significant bits. These will all be 2 raised to a power. The power starts at 0 and increases from there. So our least significant bit is 2 to the 0th power. Then 2 to the 1st power. Two squared. Two cubed. Two to the 4th power. 5th power. 6th power. And 7th power. Next comes a little bit of math. We're going to multiply each bit by the number that it's associated with. Since 0 multiplied by anything is 0, we can ignore these bits right here. Next, we simply add these values together, keeping in mind that 2 to the 0th power is 1. This gives us the number represented in binary. Which in this case is 65. Now that's nice and all, but how do these numbers represent letters and punctuation? Well, I'm glad you asked. By itself, binary only represents numbers. However, quite often binary is encoded with some predictable scheme in order to give it more value. One such popular scheme is the ASCII table. This table maps every 8 bits to a specific character. If I were to tell you this number were ASCII encoded, we could then just go over to this table and look up the value 65, which turns out to be capital A. Let's do another example. I'd encourage you to pause the video and try this out for yourself. First, we assign our values to each bit, keeping in mind that the rightmost bit is our least significant bit. Then we multiply through. And lastly, we add the numbers together. This time, we get a value of 98. Looking that up on the ASCII table, we see that it is a lowercase b. It's at this point that I want to point out some useful observations regarding binary in general, and ASCII encoded binary specifically. The first is regarding the least significant bits. It is so called because it has the least effect on the value of the binary number. Since it represents a value of 2 to the 0, it can only change the value by 1. Every bit after that can change the value of the number by a greater amount. The second is regarding these 3 bits right here. I can't say whether it happened this way on purpose, or if it is a happy accident of the way the ASCII table is put together. But these 3 bits can give you an idea of what you are looking at. Notice that for our first example, started with 0, 1, 0. And our second example started with 0, 1, 1. It turns out that all uppercase letters in ASCII start out with a 0, 1, 0, and all lowercase numbers in ASCII start with a 0, 1, 1. Furthermore, the next 5 bits are the same between upper and lowercase letters. This means that you can toggle between upper and lowercase by switching this bit right here. I should note that just because a number starts with 0, 1, 0 or 0, 1, 1 does not guarantee that it is a letter, but it is a pretty good indicator. Now, it is nice to be able to translate from binary into something a human can understand, but it isn't exactly a quick process. You can get much faster at this, but consider a message like this. Would you want to translate this by hand? Luckily, there are plenty of tools online that can handle this for us, so there isn't usually a reason to have to translate this by hand. For example, if I run this short message through a translator, this is what I get. So now that you know how binary works, what's next? You could pretend to have intellectual superiority over your friends by taking 5 minutes to type out a message entirely encoded in ASCII binary. In all seriousness though, knowing how binary works is incredibly useful for programming, computer design, and logical circuits. There are a lot of incredibly useful things that can be done with binary. This video provided that foundation you need to take this further. Did you find this video useful? Let me know down in the comments below, and thank you for watching.